Welcome to the course of Network Protocols. I'm your instructor Zishan Banglish. This is lecture number 19, and today we will be talking about interior gateway protocols. So let's move to the outlines of our today's discussion. As far as interior gateway protocols are concerned, these are basically the routing protocols. So in our today's discussion, at the very start, we will be talking about the basics of routing, and then we will be discussing about the routing policy method and the classification basically of routing, particularly the internet routing. Then after that, we will try to differentiate between the autonomous systems and domains, and particularly we will try to classify the categories of algorithms, the routing algorithms that belongs to the autonomous systems and domains, and the inter-autonomous system routing algorithms. Then we will be discussing in details about the inter-domain routing protocols, and in particularly we'll be talking about routing on a graph. We'll discuss in detail about the link state routing, and we'll study digestible algorithm with the help of an example in our today's discussion. So let's move to the first outline. That's about some basics and some concepts about the routing and particularly the policy related issues. Now let's look into the diagram in which you can just see that there are different nodes that are connected, and it's a form of an internet or a graph shape in which there are multiple paths or routes from any destination or from any source to any destination. However, the cost of path in the form of values written on the edges have been mentioned. So that value may be the congestion level, that value may be the uh, cost on that link, that may be the delay. So we will be discussing in details when we'll be classifying the different routing algorithms. About routing, so the main concern basically is that the purpose is to ensure that the information or the data or the service which we want to uh, gain, or which the data which we want to transmit needs to be delivered to the destination, and that needs to be delivered to the destination at the level of performance which we are expecting. So the performance or the level of performance, that depends upon the organization to organization, or depends upon the scenario to the scenario. The performance might be perceived as the latency, or it might be perceived as the uh, as the shortest way. So that depends upon the scenario or the class of the algorithm or the routing algorithm for which we will be talking about. Now about that forwarding. So basically the purpose of routing is to perform some basic information in order to route that packet from the source toward the next hop towards its destination. So before routing, this intermediate nodes, or any node that is basically to process that data, that have some basic information, so that on the base of that basic information, it processes that received data, and according to the available information, it moves this information to any of the link, uh, or to any of the path towards its destination. So the forwarding mechanism is taken place, that there is a forwarding table, and that's basically move information from input port to the output ports of the router. So this is a mechanism. However, for this forwarding, some basic computation or some processing is involved at the intermediate level nodes. Now, it's basically the local mechanical operations that will be taking place. About that routing, it's basically acquires the information that are available with the router, or with that intermediate node, in basically forwarding the table that have the required knowledge of the network. So this knowledge about the network, or that data that is about that have information about the complete network, its route information, that needs to be available with each and every intermediate nodes, so that the path information or the topology of the network uh, must be helpful in selecting the best route while the routing algorithm perform some basic operations. So for that, this routing, it basically requires distributed coordination of the different routers that are part of the complete network, whether they are part of the domain network, or that's basically the part of different networks that are coordinating. Now let's again consider this diagram, in which the different nodes are connected to each other uh, as a graph, and this graph is basically a weighted graph, and from every source or towards the destination there are multiple paths. So about that policy matters, the given alternative paths, how to route the information to the destination, that is known as basically the policy decision. So let's consider that if you are at node number B, and your destination is toward F, so you have two paths on which one of the path is selected uh, to transmit data or to move that data towards its destination. So this is basically the policy decision of that routing algorithm, that the selection of that path is based on some criteria. So every routing algorithm have a policy decision. Now, what are different possible policies? So one of the policy while deciding a route is basically the shortest path. So two algorithms, which is the RIP and OSPF. RIP stands for routing internet protocol, and OSPF is basically the open shortest path first. It is one of the possibility. Another possibility is based on the balancing the load on each link. So that policy has a criteria of making the network a load balanced network. The third is basically the routing is performed in order to maintain quality of service on particular links. So these are the three different policies, keeping in view which the different routing algorithms are designed or implemented. Now about internet routing, it's basically this internet routing has two levels of hierarchy. And the first level is basically the lower level, which we call it as ASS, or autonomous systems. And the second level is basically the inter-autonomous. So what about that autonomous systems? It's basically the region of the network that is under one administrative domain. So we will be looking into the diagram in which graphically the autonomous systems will be shown in the upcoming slide. and then each autonomous systems that has independent intra-domain routing protocol. So different autonomous systems within a network might run different routing protocols. One of the inter-domain routing protocol is basically the RIP, which is a distance vector routing information protocol. There's another type of protocol that work on a different criteria. That's the link state routing protocol, and we have a perfect example of OSPF, which follows into this link state category. So what is the difference between these two? We will be discussing it in the upcoming slides. Now, the second level after the autonomous systems, which is the first level, is the interconnected autonomous systems. And between the different domains or the autonomous systems, there are different protocols that integrate different autonomous systems. And one of the protocol for inter-domain or inter-autonomous system coordination for routing purposes basically the BGP, which is the Border Gateway Routing Protocol. This BGP protocol will also be discussed in the upcoming slides and sessions for the routing protocols. Now, let's consider this diagram in which you can just look into it that this is one autonomous system in which there are two different nodes, and they are connected through each other, and there are a lot of different intermediate nodes, and towards this destination from that source there are multiple paths. So it's a sort of graph. Similarly, there is another autonomous system or a domain system, which is then AS3, which is a graph shape, and another autonomous system which is AS2. So each autonomous system, it is possibility that in this autonomous system the distance vector routing algorithm will be maybe used for routing purposes, and it is perfectly possible that the link state routing algorithm might be used in this autonomous system. However, there are different category of routings between the inter autonomous systems. So border gateway protocol or some other gateway protocol are basically used for inter or between the different autonomous system communication. Now, why we need the concept of autonomous systems, or basically the domain, and the basic purpose is that the algorithms are not so much effective, particularly this routing algorithm, that it may cope up with the large network, or if the size of the network increases, so the capability of that routing algorithm also decreases. So a routing algorithm that is capable of managing the entire internet or a large part of the network, that is not possible. So for that we need the concept of autonomous systems, or we can say that the whole network is divided into sub networks, or we can call it a domain, and then each domain have different type of routing algorithm, or there may be the same routing algorithm that may be that would be that might be executing on each domain. And the another aspect is that why we need it domains is basically that the different organization or the networks that are part of the different organization that may have their different internal routing policy. So some of them may be preferring the distance vector criteria for route selection, preferring for the link state routing. So the policy or the policy decision changes with respect to the organization and to their interests. Now, another aspect for this introducing the concept of autonomous system is that most of the organization try to hide their network configuration, internal network configuration from the outside world. They want to create an abstraction, and for that they need a subdomain or a domain environment. And similarly, all the organization has to choose how to route across multiple organizations in order to integrate and in order to be compatible in the complete network environment. So for that, the concept of autonomous system is of importance. Now, uh, basically, it's very easier to compute routes, and it's more flexible, and it's more autonomy and independent way. Now again, consider this diagram in which you can just look into it that it's a sort of graph, or we can call it, if we can review from the knowledge of data structure, so it is basically a weighted graph, or we can call it an internet in which the different nodes or different part of the networks are connected to each other. Now, in order to determine a good path through the network from the source to a destination, so the routing is basically used. And you can just look into it that the network is modeled as a graph, and we have uh, routers, these which are basically the nodes. These are basically the intermediate nodes, and the links, we can call it, these links we can call it the edges. And the cost which are which is written on each edges, it may be the delay, the time of the delay, or it may be the level of the congestion, that how much traffic is on that link. So different organization uh, consider different meaning of modeling that network in order to calculate the best route towards the destination. Now, basically, in case of inter-domain routing protocol, it's basically an unreliable data delivery. Yes, we already know that from our previous knowledge, or from the basic concepts of routing. When we consider the distance vector, it's basically is the example of that distance vector routing algorithm, and it's basically based on the Belford algorithm. We have already discussed this in the course of data structure, and in which every node in the network tries to exchange some information, some basic information, and that information is about its links value towards to all its neighbors. And it's basically a less complex type of algorithm because very low overhead is involved in a communication. However, it have a drawback that it takes long to converge, because that is in proportion to the maximum path length. It takes times. Another routing protocol, inter-domain routing protocol, is a link state routing protocol, in which OSPF is a perfect example, and we already discussed the Digestra algorithm in the course of data structure. So this OSPF is based on that algorithm, and it's basically uh, works on the mechanism of flooding, and that each router with time to time floods information to all the other routers, so that they may move the information about the topology of the network on all its interfaces. So the drawback of this link state is again that it's a very communication and computationally and a challenge. So if we are trying to consider this link state type of algorithm in a network that are very resource constrained, like wireless sensor or a body wear networks, so it will be a very challenging job. So that they may not be these algorithms, this link state algorithm may not be feasible for implementing in such type of networks. So the goal of routing is basically to find a good path from the source to destination, and another thing is that uh, good is oftenly considered as the shortest path. However, the good path may be that path that have a low congestion, or where the error rate is low, or where the uh, where the destination route may be shortest. So we can just look into it that we have already talked that the network is modeled as a graph, and the cost means delay or the congestion level. Now, in case of link state routing, we already discussed this, that it works on the mechanism of flooding, that each node already know its connectivity and cost to its direct neighbor. So in that case, consider here B is the direct neighbor of A, and A knows its direct cost towards B, which is 2, and similarly it knows its direct cost toward D, which is 1. So here the OSPF works on the mechanism of flooding. So every node tells every other node that this local connectivity cost information, that is why flooding, it sends this information to the other nodes that are connected. Now at the end, every node learns the complete topology of that network. So when this OSPF algorithm, which is the digester algorithm, executes, so after its execution, every node knows the link information or the link cost information of every other nodes towards its neighbor directly, or toward itself indirectly. So let's consider that that A is connected to B and the cost is 2, and A is connected to D and the cost is 1, and A is connected to C. This is C is indirectly connected, and the cost is basically A is connected to C and the cost is basically 5. So 1 2 1, and this the cost is 5. For example, if there's a direct connection, direct link, and there's if the indirect cost is 1 into 3, that is 4, and another way is 1 2 and 3, so this is 6. So but the direct cost from A to C is 5. Now every nodes periodically generate link state packet. We call it an LSP, and this LSP contains ID of the node. It contains the list and details about the direct neighbor and along with its cost, and it includes the uh, sequence number, which is a 64-bit number, and the last field is the time to live, so that the redundant packets or the unnecessary packets can be killed in the communication in order to avoid the congestion. Now, flood is reliable. It uses basically the acknowledgement and retransmission mechanisms, and basically this why to use this sequence number. It's basically in order to identify the new link state packets, and so that the older LSP may be killed. So an older LSP, as I have already discussed, if the new LSP received, so the older LSP is discarded. And there's again a question that if the router crashes and the sequence number reset to 0, so what will happen? So basically the algorithm will execute its the topology of the network completely, that the algorithm will re-execute itself. So receiving the node flood LSP to all its neighbor, that's except the neighbor where the LSP came from. So this is the mechanism on which that flooding works, that the node that is receiving that LSP, it forwards to all the neighbor except it from the node from which where it receives. So let's consider this example, that how this flooding works. So the information is communicated to the direct links, And from here, this information is further communicated. You can just look into the diagram that the information is connected to the direct neighbors, which is received by 2 and 3, and similarly the information is propagated to the complete network. So the flooding is basically performed from level to level to all its intermediate nodes, as shown in the diagram. So this is the complete flooding, the information about 1 and its link information towards 2 and 3 and the cost details has been flooded to the complete network. Similarly, the other nodes will completely perform this flooding operation in order to share the topology with all the network. When this link state algorithm will ends, so every node will know the complete topology of the entire network. Now let's look into the link state routing algorithm. That's the Dijkstra algorithm. So how that is that performs its operation. So basically, in the first phase, uh, the network topology and the link cost is basically known to all the nodes. So that's a sort of prerequisite type of thing. And it's basically a link state flooding is performed in order to share this information, this link cost information, to all the networks. Now all the networks after this flooding will have the same information, and then after that, when a packet is originated for sending it to the receiver, so a computation is performed for in order to calculate the least cost from one node, that will be the source node, to all the other nodes. We'll be looking into diagrammatically in the upcoming slide that how the least cost is calculated stepwise. There are some, and then the whole process is repeated for all the other sources. There are some notations that needs to be considered, that C of I and G is basically it's the cost information or the details about the cost from I is basically the source or the and J is basically the next intermediate, or it might be a destination. So if this cost is infinite, so that means that the J is not the direct neighbor, it might be the indirect neighbor. Another thing notation is the DV. It's basically the value of the cost of path from the source to that node V. Now the PV is the uh, predecessor node along the path from source to V. So it's that's the next to V. So this is basically the function that calculates the predecessor node. And similarly, the S, it's basically a group of nodes or a set of nodes whose least cost path definitely is known to the network. So we can call this Dijkstra algorithm that works on the mechanism of greedy algorithm. So that's initialized, and this is a set of that nodes that have the least cost, and then a loop is executed, and on the base of that loop, the cost is calculated here. And on the basis, just look at to it that it's basically, if the V is adjacent to it, then that means that it's basically the direct neighbor, otherwise it's an indirect neighbor. And for all that thing, the cost is calculated and is stored in a vector, and then at the end, in this Dijkstra algorithm, again a loop is performed that will calculate the lowest path from the destination, from the source toward the destination, and that is executed, and this loop will continuously execute on all the nodes. You can just look into it that the loop is executed until all the node in the set in that domain is executed, and for that it will calculate the lowest path. Just look into it. We are going to explain this thing diagrammatically, that if starting from the node A, which is the starting node, and which is the A, and towards the B, the path is basically, the cost is basically 2, and from that node towards the C, which is C, the path is basically 5. It's basically the direct path. Similarly, from that node A towards D, the path is basically that 1. The cost of that path is come. Similarly, from A to E, so E is basically not the direct, so we can specify here as that it's an infinity, which clearly shows that from A toward E, so this E is not the direct neighbor. Similarly, F is not the direct neighbor. So the first part of that digestive algorithm, it will assign the values as shown in the table. Similarly, the last part, it is when executed, and it will calculate it for all the remaining nodes until all the nodes in the S are shown. So it will calculate for the from the above states, the least set is basically that D node, which have a cost value of 1. So from that D, it will again execute this algorithm, and it will calculate the values, as you can just look into it as shown in the table. That's basically the row number 1. And similarly, this algorithm is executed, and it will calculate for E, because E is the shortest path. E has the shortest path. You can just look into it that among the 4D, 2D, and infinity, this is the least path, and this algorithm will execute until and unless the destination is reached. So you can just look into it that when the complete all the nodes are processed, so the shortest path from the source A towards destination F is calculated, as you can just look into the table that how this algorithm is executing. So this was all about it was about the link state algorithm, and inshallah ta'ala in the upcoming lecture we will be talking about the distance vector algorithm, and we'll talking about the RIP, routing internet protocol. This is the reference from which the content has been taken, and you can just consult it for further details. So thank you very much for patiently listening. Take care. Allah Hafiz.